Hi everyone, Dr. Burns here with our lesson on energy and energy changes. We'll also be talking about heat in this video. So we've talked previously about chemical reactions. Back in General Chemistry 1, we learned how to balance them, identify their different types and all the different things that they do. And now we want to talk about the energy associated with those reactions. So chemical reactions and their accompanying changes in energy are important parts of our everyday world. Some examples of this are reactions involved in the metabolism of food, right? Food provides us, our body, with energy, so we need to eat in the morning so we have energy throughout the day. We also have the burning of fossil fuels such as natural gas, gasoline, and coal, which help us, with our cars, driving our cars, heating our buildings, and many other applications. And then we also just have the production of useful products from raw materials. So let's review something that we learned in General Chemistry 1. Which of the following is a chemical change? So we learned about two different types of changes, chemical and physical changes. We say that physical changes are ones where the substance is still the same, it's just in a different form, whether that's a solid, liquid, or gas. The chemical change, we see a physical chemical reaction happening. So look at these 5 options here and think about which one of them is a chemical change. Our options are the combustion of gasoline, the melting of snow, the evaporation of ethanol, and the sublimation of CO2 at room temperature. The answer for this one is A, the combustion of gasoline, where we take gasoline, which is a carbon and hydrogen containing compound, we react it with oxygen, and we create CO2 and water in order to use in our car engines. When we look at these other options, like the melting of snow is what? Water, H2O. When snow melts, it's still water, it's just in a different form. So we're going from water in a solid form to water in a liquid form. The same goes for the evaporation of ethanol. Ethanol, let's call it ETOH. There's carbon, there's hydrogens, and there's an oxygen group in there. When we're looking at the evaporation of ethanol, we're saying we start with ethanol liquid and we turn into ethanol gas. It's still ethanol, but it's just in different physical form. And finally, we have the sublimation of CO2. Remember, sublimation is when we go from a solid to a gas. So we have CO2 solid turning into CO2 gas. We're just changing phase in that reaction. So energy is the capacity to supply heat or do work. And we have 2 types of energy. Potential energy, which is the energy an object has based on its position, and kinetic energy, which is the energy an object has based on its motion. We also have the law of conservation of energy, which tells us that during a chemical or physical change, energy cannot be created nor destroyed. Only its form can be changed. Okay, we can't just pull energy out of nowhere. If we could, then we wouldn't have to use gasoline for our cars or anything like that. So we can only transform energy into different forms. We cannot create it and we cannot destroy it. Along with that, thermochemistry is the study of heat in chemical reactions, where heat is the transfer of thermal energy. So it's a type of energy, just dealing with thermal energy specifically. Heat is either absorbed or released during a chemical process. The SI unit for heat and energy is joule. A joule, which we denote with the character or this variable J, is the energy unit that we will be using. We can also use the unit of calories, which you may hear when you're thinking about food. So often calories are used, And 1 calorie is defined as the amount of heat required to raise 1 gram of water by 1 degree Celsius. We'll use calories more so later in our lessons when we talk about calorimetry, as that pertains more towards food when calories are more pertinent. But we will be able to convert between calories and joules using the 2 conversion factors we have at the bottom of our slide here. So to go between a calorie and a joule, we use this conversion factor here, where 1 calorie is equal to 4.184 joules. Our second conversion looks a little confusing because it says that 1 calorie is equal to 1,000 calories, which, as we know from conversion factors, doesn't make any sense. The big difference here is in the uppercase or lowercase c as we define calories. So lowercase c is the calories that relate directly to joules. Okay, that's what we use down here with our conversion to joules. An uppercase c is for calories that we use for food. And this is because a capital C calorie is equal to a kilocalorie. So capital C calorie is a kilocalorie. We use the capital versus lowercase c notation for calorie because when we're relating it to food, when we want to say something has 100 calories in it, well, if we were to put that into kilocalorie value, or into regular calorie with lowercase c, that would be like 100,000 calories, which seems even worse than 100 calories actually is. So the uppercase C calorie and the relationship it has to a kilocalorie is strictly because of how we relate calories to food. So if you look at a food wrapper or an energy drink that's nearby to you right now, and you look at the calories that are listed on the nutrition facts on that packaging, the calories that you see are actually in units of kilocalories, not calories as we relate them to joules. So we got to keep that in mind, that 1 capital C calorie is equal to a kilocalorie, and 1 lowercase c calorie is related to joules. So let's practice using these conversions, and we'll just add our extra conversion here that this is 1 kilocalorie. Okay, so a reaction releases 421 kilojoules of energy. How many calories and kilocalories does this correspond to? So we're looking to convert kilojoules to calories, and then as well to kilocalories, which we know are uppercase C calories. So the first thing that we're going to want to do is use this conversion factor, the calories to joules relationship. However, the number that we're given is in kilojoules. So our first conversion that we're going to have to do is go from kilojoules to joules. Once we have joules, we can go from joules to calories. And once we have calories, we can then go to kilocalories. So let's start with taking that 421 kilojoules and converting it to joules. Well, we know that kilo, the prefix kilo, corresponds to 1,000 of the base unit. So we know that in 1 kilojoule, there's 1,000 joules. So that's our conversion for joules to kilojoules to joules. Let me get my calculator out so we can do our calculations together. Okay, so we're going to take 421 and multiply that by 1,000. And we're going to get out 421,000 joules. Now that we have joules, we want to convert to calories using the conversion factor we have up here. So in order to cancel out our units of joules, the 4.184 joules is going to go on the bottom, and 1 calorie is going to go on the top. And as we can see, joules will end up canceling. And what we'll get out, we'll take that 421,000 and we will divide it by 4.184. And that gives us 100,621 calories. So that answers our first question of how many calories are in this amount of energy. However, we have to think about our sig figs. We're never going to be forgetting about sig figs. They will always be around. So our original value had 3 sig figs. So our calorie value in 3 sig figs, we're going to need to put this into scientific notation, is 1.01 times 10 to the 5 calories. Our next step after we get to calories is then convert to kilocalories. So we know that 1 kilocalorie has 1,000 calories. So we'll take that 100,621 calories, and we'll put the 1,000 on the bottom because that goes with the lowercase c calorie. And we'll put 1 kilocalorie on the top. That way our units cancel, calories will end up canceling, and we're left with units of kilocalories. So we'll take that 100,000 and we'll divide it by 1,000, and we get out 100.621 kilocalories. With sig figs, this would be 101 kilocalories, which you could also write as 101 capital C calories. It's hard to tell the difference between uppercase and lowercase c's with how I'm writing it here, so I will probably just relate this to kilocalories so we know the difference between calorie, lowercase c, and uppercase c calories, which are kilocalories. So just keep that in mind as you're going through these problems in your ALEKS homework, depending on the type of calories that the question is asking for. So let's do a few more. We want to convert the following. We have 4 problems here that we're going to convert between joules and calories, or calories to joules. So our first one asks us to go from 42 kilojoules to calories, which is very similar to our previous problem. So our first step of our previous problem was to convert from kilojoules to joules, because the only way we can use the calories to joules conversion factor here is if we have our energy unit in joules already. So our first step is to take 42 kilojoules and multiply it by 1,000 joules. So we'll take 42 and we'll multiply that by 1,000 to get 42,000 joules. Now that we have joules, we can use our calories to joules conversion factor. We'll put 4.184 joules on the bottom and 1 calorie on top in order to cancel out the joules. So we'll take that 42,000 and divide it by 4.184. And we get out 10,038 calories. And with sig figs, that would just come out to 1.0 times 10 to the 4 calories. Let's just highlight that so we can see our answer. Always got to remember your sig figs. Next up, we want to go from 55.6 kilocalories to calories. So we're going to use our second conversion factor here, because uppercase C calories are kilocalories, and we can use that 1,000 calories to convert. So we'll start with 55.6 kilocalories. And in order to get to calories, we will put 1,000 calories on the top, 1 kilocalorie on the bottom in order to cancel out kilocalories. So we'll take 55.6 and we'll multiply it by 1,000 So we get 55,600 calories. Now with sig figs, we can only have 3 sig figs, so we'll put this into scientific notation to get 5.56 times 10 to the 4th calories. Okay, for these last two, I want you to pause your own video and try these two independently. So our next problem has us working backwards from our previous examples, where we're starting with kilocalories and we want to get to kilojoules. So we're going to do like we did in our previous problem up above, and we are going to take that 326 and we're going to multiply it by 1,000 to get calories. That way our kilocalories will cancel. So we're going to get 326 times 1,000 to get 326,000 calories. Once we have calories, we can then convert to joules using our 4.184 on the top and 1 calorie on the bottom, so calories cancel. So we have calories here, calories there. So we'll take that 326,000 and multiply it by 4.184. So we get 1,036,3984 joules. Now that we have joules, we will just divide by 1,000 in order to get to kilojoules. So we'll just divide this by 1,000 to get, with sig figs and in scientific notation, 1.36 times 10 to the 3 kilojoules. Okay, and for the last one, we're taking similar steps as our previous problem, but we're stopping at joules. So we're going to take that 25.6 kilocalories, multiply it by 1,000, and once we have calories, we can convert it to joules. So we take 25.6, we're going to multiply it by 1,000, and then multiply it again by 4.184. And with sig figs and scientific notation, we get 1.07 times 10 to the 5th joules. So there are 4 answers for these problems for conversions. So now we're going to talk more about thermal energy and how it relates to temperature. Thermal energy is a type of kinetic energy associated with the random motions of atoms and molecules. So we call it thermal energy because it has to do with heat. And we know, back from when we started learning about atoms and molecules, is when we increase the temperature, the molecules are going to be moving faster, and if we decrease the temperature, the molecules are going to be moving slower. So temperature is a quantitative measure of something that is hot or something that is cold. Specifically, fast-moving molecules have high thermal energy, meaning they would be considered hot. Slow-moving molecules would consider having low thermal energy and would be considered cold. So let's think about this. In which of the following would the particles be moving most rapidly? Would that be ice at negative 20 degrees Celsius, water at 20 degrees Celsius, steam at 110 degrees Celsius, or boiling water at 100 degrees Celsius? Well, particles that move most rapidly would have the highest thermal energy. And if they have the highest thermal energy, they would be considered the hottest. So out of all of these options, steam is the hottest because it has the highest temperature. So highest temperature is equal to the highest thermal energy. Okay. So we're going to talk about heat a lot in this chapter. Heat is denoted by the variable Q and is the transfer of thermal energy between two bodies at different temperatures. Heat flow describes the flow of that thermal energy from one body to the other. Increasing the thermal energy of one body thus decreases the thermal energy of another. When two bodies are placed in contact, energy will flow specifically from the higher temperature to the lower temperature. So the natural flow of heat is always from highest to lowest. So if we have something that's hot, which I'll show as red, and we place it next to something that is cold, we are going to see the hot object transferring its heat to the cold object when they are placed in contact with each other or near each other. So this will continue until an equilibrium is reached and they are both at the same temperature. Now this flow of energy, this heat flow, is natural for everything. We will always see higher temperatures flowing to lower temperatures. So a meme that I really like to show my students is this one. Someone is saying, I'm sorry for letting the cold in, but really you can't let the cold in because you're letting the heat out. So if someone ever says, sorry for letting the cold in, you could say, you're not letting the cold in, you're just letting the heat out. I learned that in my chemistry class because that's how thermochemistry works. So just remember that. Okay. Now, when we're talking about this transfer of heat, where the heat is going, all of the different energy changes, how we're transitioning energy, we have to think about two things: the system and its surroundings. So the system is a part of the universe that is of specific interest. So that's the ice cube that you're leaving on the counter to melt. That's the hot piece of metal that you're putting down next to a cold piece of metal in order to transfer the heat between the two. Okay? Usually the substance that's involved in the chemical or physical changes is going to be considered the system. The surroundings constitute the rest of the universe outside the system. So if you're putting an ice cube on the counter and letting it melt at room temperature, the system would be the ice and the surroundings would be everything around it: the counter, the air around it, the kitchen, the rest of the universe. Okay, everything that surrounds your system of interest. Okay, the system plus the surroundings is what we call the universe. I'm not going to talk about the universe in some deep philosophical way. We're just going to think of it as the rest of the world around us, okay? We're not here to get deep about physics and astrophysics and everything else, like what makes up the universe. We're not doing that. We're just going to consider the system as what we care about, and the surroundings is everything that's around it. And when we add those two things together, those are going to equal the universe. So when we have heat that's being transferred between the system and the surroundings, we have different processes that can happen. The first is an exothermic process, and this occurs when heat is transferred from the system to the surroundings. And a big example of this is the Hindenburg accident. Anything that really explodes is going to be exothermic. We have heat that is being transferred from the system, so in this case the Hindenburg, as it's reacting, okay, that's where all the chemicals are that are reacting with each other and exploding, okay? It's being transferred, the heat from that explosion is being transferred from that system to the surroundings, okay? And our to's and our froms are going to be very specific for what we're talking about with heat, so we need to get used to talking in that language. So an exothermic process is when heat is transferred from the system to the surroundings. Now the way I like to think about this is we have exo, exo, like exothermic, That also relates to explosion. Explosions give off heat, so whatever is giving off the heat is the system and everything else is the surrounding. It's warming up the surroundings. So we're transferring heat from the system to the surroundings. Our next type of process is an endothermic process. And an endothermic process is the opposite of an exothermic, and this occurs when heat is transferred from the surroundings to the system. So we're taking heat from around us, around whatever our system is, and we're placing it into the system in order to transfer the heat that way. This is what happens when you have cold packs. So in order for them to feel cold, heat has to be removed because the removal of heat is something getting cold. Okay, so we have a reaction that's endothermic. It's taking heat from the surroundings and putting it into that chemical reaction, causing the surroundings to decrease in temperature, meaning the cold pack gets cold. Okay, and that's why we're able to crack it open. When we crack it, that's that chemical reaction happening, and that's how it gets cold, is that it's taking in the heat from the surroundings, therefore the surroundings are getting colder. There's no fun word way that I can help you remember endothermic. So if you just remember that exothermic is heat being given off to the surroundings from the system, then you can remember endothermic as just the opposite of that, because there's only two of these types of processes. Okay, so let's just quickly review. Let's look at our options here for this question. An endothermic reaction causes the surroundings to do what? Warm up, become acidic, expand, decrease in temperature, or release carbon dioxide. Choose your answer and put it in your notepad. Okay. So now that we know about where heat is going, how heat is moving between our system and our surroundings, we can start to talk about something called thermodynamics. Thermodynamics is the study of the interconversion of heat and other kinds of energy. In thermodynamics, there are three types of systems. The first one is an open system, which can exchange mass and energy with the surroundings. So here I have a flask filled with water, okay, and the top of the flask is open. So in our natural world, if we were to leave that open, we would see that water vapor could go in or out of that flask. Okay, that's what we're seeing here, water vapor moving in and out. But we also know that if we took that flask and put it onto a hot plate and heated it up, we would be able to transfer heat to the liquid. Okay, so within that flask, heat could go in, but we could also cool it down and have heat go out. We then have a closed system, which allows the transfer of energy, but not mass. So all we did in that situation is we put a top on our flask. So we closed the system. We closed it up so we can no longer transfer mass. If I were to flip that upside down, water wouldn't be able to leak out, and no water vapor can get out or in either. But we can still transfer thermal energy in a closed system. So again, we could heat it up on a hot plate and allow heat in, or we could cool it down in an ice bath and allow heat out. Our last type of system is an isolated system. So it does not exchange either mass or energy with its surroundings. So not only do we have a top on our flask, we also have this kind of insulation around it so that heat cannot be transferred in or out of that system. So of our three systems that we have here, an open, a closed, and an isolated, what I want you to do is think of an example of each type of system, open, closed, and isolated, that you know from daily life. And I promise you probably have one sitting very close to you if you're watching this at your desk. Okay, so think of an open system, a closed system, and an isolated system. I personally like to think of, still going with the water example, a glass of water that's open to the rest of the world would be an open system. A water bottle would be an example of a closed system, like a plastic water bottle where I can close the top off, but if I left it in my car, it would probably get hot on a summer day or cold and frozen on a winter day. And an isolated system similar to that would be, like a Stanley water bottle or a Hydro Flask water bottle where it has insulation around it. So if I put ice in there, it would stay cold for a lot longer than if I were just have a regular water bottle. So those are very common types of open, closed, and isolated systems that we see in our daily life that all have to do with the transfer of mass and the transfer or lack thereof of heat. Okay, so a few more definitions before we get into more of our lesson here. We need to talk about these things called state functions. State functions are properties that are determined by the state of the system, regardless of how that condition was achieved. The magnitude of the change depends only on the initial and final states of the system. So I have this example here of a building. Okay, so let's say you're going to the doctor's office and you walk in at the ground floor and you have to get to the 4th floor. That's where your doctor's office is. You need to get there by 12 o'clock in order to get to your appointment. So you need to get to the 4th floor by that time. There are many different ways that you could choose to get to the 4th floor. You could start at the ground floor. You could, let's change my color here, you could walk up to the 2nd floor, walk up to the 2nd floor, walk up to the 3rd floor, walk up to the 4th floor, and you'd get there. You could go into the building and you could take the elevator. Let's call these windows elevators. You could take the elevator all the way up. You could take the stairs from the ground floor to the 2nd floor, and then from the 2nd floor you could take the elevator up to the 4th floor. You could take the elevator all the way up to the top floor, and then you could take the stairs down. You could, let's see, what's another really obnoxious way you could go? Let's go purple. Let's say we start at the ground floor, go to the 2nd, go to the 3rd, take the elevator to the top, go from the top floor down to the 5th floor, then take the elevator from the 5th floor to the 4th floor. No matter which route you take, you're starting at the ground floor and you're ending at the 4th floor. You're ending at the same spot. And that's what a state function is saying, is I don't care how you got between the 1st place and the 2nd place. I just care that you got there, okay? It doesn't matter how you got there. It just shows that you got there regardless. So a state function is really just, it's determined by the state of the system. It depends on the initial and the final states of that system. In this case, the initial state was the ground floor, and the final state was the 4th floor. You had to traverse 3 floors somehow to get there, whether you went up all 6 and then went down 2, or you went up 2, over 3, whatever, okay? So it doesn't matter how you got there, you got there. So examples of state functions are going to be energy. Okay, we only care about the energy before the reaction and after the reaction. It doesn't matter how it got there, but we just care about what the energy ended up being. Pressure, okay, is another state function. Volume is a state function, and temperature is a state function. And we often show state functions as having a delta. So delta E for energy, delta P for pressure, delta V for volume, delta T for temperature. Okay, whenever we see that delta, all we're doing is taking final, delta equals final minus initial. No matter what it is, energy, pressure, volume, temperature, we're taking the final value of that unit, so final energy, and subtracting it from the initial. Final temperature minus the initial temperature. So whenever you see a delta, that automatically means final minus initial. And it's very specific that you have to do final first and then initial, because that's what's going to tell us our sign. Our sign is going to matter. State functions do final minus initial, and their sign matters. We either saw a decrease in energy or pressure or volume or temperature, or we saw an increase in energy, pressure, volume, or temperature. So we always do final minus initial. Okay. So with thermodynamics comes some laws. Now we'll talk about all of the laws of thermodynamics in a future chapter, but the first one is what pertains to what we are discussing right now with heat. So the first law of thermodynamics states that energy can be converted from one form to another, but cannot be created or destroyed. Very similar to the law of conservation of energy. So here we express the first law of thermodynamics as delta U of the system plus delta U of the surroundings has to equal 0. It always has to equal 0 because there cannot be any change in the overall energy of the universe. Delta U is our sign for internal energy. We use U here because E, if you remember back from General Chemistry 1, was specific to our energy of different energy levels in an atom when we were talking about wavelengths and frequency and energy. This is a different energy. Internal energy is different from that energy, so we denote them differently. So instead, we use U instead of E. So U is just internal energy. It's just another form of energy. So we see delta U of the system plus delta U of the surroundings, so the internal energy of the system plus the internal energy of the surroundings must always equal 0 based off of the first law of thermodynamics, that energy cannot be created or destroyed. And again, here we have where delta U is the final minus the initial, so the difference in the energies of the initial and final states. Therefore, internal energy is a state function. So as we said in our previous slide, energy is a state function. Energy has many different subsections of energy. So specifically, internal energy is one of those energy-related state functions. So how does this relate to heat? Well, it also relates to something that we call work. So the work then has to be done on the system overall because of the change in the heat. So the overall change in the system's internal energy is given by the equation delta U is equal to Q plus W, where Q is heat and W is work. An example of work in a type of chemical reaction would be like a change in volume. And we'll talk about work specifically more in a future lesson. But for right now, all we need to know is that delta U is equal to Q plus W. So here, what we're talking about specifically is the delta U of the system, and not so much the delta U of the surroundings. So we're talking about heat and work, how they affect the system specifically. So what I want to do next is look specifically at this image and discuss how work and heat relate to the system, whether that heat and work is going into or out of the system, and how that relates to the overall energy of the system itself. So let's first look at when heat flows in and work is being done on the system. So if heat flows into the system, so if we're putting heat into the system, that would be an endothermic reaction. Okay, work is done on the system and the internal energy would increase. Next, if we look at the second half of this image, if heat flows out of the system, which would be an exothermic reaction, work is done by the system, and therefore the internal energy would then decrease, because if I'm doing work, I have to give off energy. Now, as I said before, this language of something doing, heat being transferred to the system by the surroundings, to the surroundings by the system, to and by, in and out, these are all very important language for what we're talking about with energy. So to kind of summarize it in a table, here we have a way of telling us if Q and W are going to be positive or negative based off of that language. So when I say that heat is absorbed by the system, specifically the term we're looking at there is going to be absorbed. So heat is absorbed by the system, which is an endothermic reaction. We are going to say that Q is positive as it relates to what we just talked about when heat was going into the system, and we said that was an endothermic reaction, and overall the change in internal energy was positive, or it increased. Okay. On the opposite side, if heat is released by the system, that's an exothermic reaction. Okay, remember exothermic explosion, we're giving off heat. Okay, heat is released by the system to the surroundings. Therefore, Q would be negative. Okay, we're decreasing the amount of heat from our system and increasing it to the surroundings. So we're giving it off. For work, we say that if work is done on the system by the surroundings, so here it's on the system by the surroundings, okay, an example of that would be a volume decrease, then W is positive. However, if we say work is done by the system on the surroundings, an example being a volume increase, okay, so by the system on the surroundings, W is then going to be negative. So what we can do is we can use this notation and this language of being absorbed, released, on the system, by the surrounding, by the system, on the surroundings. We can use that to tell us how the internal energy is going to change for a given system, whether we're given values to calculate that or not. So let's look at a few examples of this. So consider an internal combustion engine. Here, so like in our car, think of your car. You have an engine, you turn it on, you put gasoline into your car, you turn it on, the gasoline is going to start to burn, and it's going to start moving the pistons in your engine and all the different belts and everything like that, okay? All that's going to start working. So the system here is going to be the gasoline. That's the reaction that we care about. That's what's going to be giving off the energy, giving off the heat in order for all of those things to start happening. So the system is the gasoline and the oxygen that's reacting with. The surroundings is then the rest of the universe, so your engine, your car, the road around you, the trees around the road, everything else around your car and your engine. Okay, so this reaction we know is exothermic, right? Where there is many explosions going on in our engine as it's going. Okay, it's giving off heat, right? You're done driving your car after 20 minutes, you feel the hood, it's hot. It's because it's giving off heat. So it's an exothermic reaction. So heat is being given off to the surroundings. Heat is being released. So that's that language there. Heat is released to the surroundings. Therefore, Q would be negative based off of our table. If heat is released, Q is negative. The reaction itself pushes the pistons out, so work is being done on the surroundings. Remember, our engine is our surroundings because our system is just the gasoline itself reacting. Okay, so the reaction is going to push those pistons out, so work is being done on the surroundings. Okay, we're seeing an increase in our volume. The volume of the pistons is changing. Okay, so our work is then going to be negative. So based off of our delta U expression, delta U is equal to a negative Q plus a negative W. Therefore, overall, the internal energy of the system is going to decrease. So we see a negative delta U value. Okay, so let's put some numbers to this. So let's practice with some numbers. So calculate the overall change in internal energy, delta U, in joules, for a system that absorbs 188 joules of heat and does 141 joules of work on its surroundings. So when we're looking at problems that have to do with change in internal energy, heat, and work, we have to look at the language in the problem itself. The language is going to tell us the signs of Q and W. The value of Q and W in the problem itself does not tell us our signs. Okay, so you have to use the language of the problem to predict your signs. Okay, so we have Q and W. We know that Q is 188 joules and W is 141 joules. Now my signs are not correct yet. I can't just plug this in yet. We have to look at the language and how it relates to the sign. So the problem says that the system absorbs 188 joules. So we go to our little chart, our table, and it says that when heat is absorbed, Q is positive. So that 188 would be a positive value. Now for work, it says that 141 joules of work is done on its surroundings. So we have two options, by the surroundings and on the surroundings. Well, the problem says on the surroundings, so W would be negative. So this would be negative 141 joules. Signs matter. If there's one thing that's going to bring us through the rest of general chemistry too, it's that signs will always matter. Because with state functions, which we're going to use a lot, that delta is final minus initial. No matter what those signs are, we're still doing final minus initial. So our signs are going to matter here. So we have delta U, a state function, so signs will matter. Q is positive 188. We'll put a positive there. We'll add to that negative 141 joules. So we plug that into our calculator as is 188 plus negative 141. We get that delta U is a change of positive 47. So we saw an increase in our internal energy. Okay, let's do a few more examples where we're using this language to predict our signs. Okay, what is the value of work, and is it done on the system or by the system when 87.33 kilojoules of heat is absorbed and the internal energy is 1,999 joules? So think about this problem. What's the first thing you should do before you even look at the language? Okay, think of these two numbers, 87.33 kilojoules and 1,999 joules. What's the first thing you should do before even thinking about the language? Then let's just highlight the language. Let's see, heat is absorbed. That's the one that we're looking for. And you want to know, is work being done on or by the system? So what I want you to do is pause the video, think of what the first thing that you have to do is in this problem before you even think about the language. What's the first thing that you have to do? Do that. Pause your video and do that. And then come back. Did you say convert these values into the same unit? Because that's the first thing that you should want to do. Regardless of positives or negatives, we're still going to have to convert something. So you could do this one of two ways. You can convert kilojoules to joules, or you can convert joules to kilojoules. It doesn't really matter. I don't specify in the specific problem what I want the answer for work to be in. If you were given this type of problem on your Alex homework, it would specify the specific units. So since I don't specify, you could do it one or the other. As long as they end up in the same units, you're good. So I'm going to convert my 1,999 to kilojoules just because I don't like using large numbers. That's my own personal preference. If you wanted to convert the 87.33 kilojoules to joules, go for it. You're going to get the same answer, just in a different unit, just off by a factor of 1,000. So either way, doesn't matter. Okay, so I'm going to take that 1,999 kilojoules. Joules. Jumping ahead there. Joules, and I'm going to divide this by 1,000. There's 1,000 joules in 1 kilojoule. So that gives me 1.999 kilojoules for my delta U. Okay, so we've converted. Now we can start thinking about the language of this problem. So we have Q, W, and delta U. W is what we're looking for. That's what we're solving for. Delta U we just found to be 1.999 kilojoules. Again, if you wanted to convert the heat to joules and keep delta U in joules as well, go for it. They just need to be the same unit, okay? So, let's see, for heat, Q, we have 87.33 kilojoules. The only thing we have to determine is the sign, because the numbers that are given in the problem don't tell us the signs. The language of the problem tells us the sign. So, what is the value of work done on or by the system when 87.33 kilojoules of heat is absorbed? So it's absorbed by the system. Absorbed by the system mean Q is positive. So this would be a positive 87.33. Okay, so we have that delta U, 1.999 kilojoules, is equal to positive 87.33 kilojoules plus W. Okay, and we're going to solve for work. So we're going to take that 1.99, and in order to solve for work, we'll subtract off 87.33. And we get that the work is equal to negative 85.33 kilojoules. So, 4 sig figs just to keep up with my sig figs for that answer. Now, I'm not done yet because the problem also asked, is work done on or by the system? Well, the answer that we got out is a negative value. So if W is negative, that means that work is done by the system. So work done by the system. And this is why our signs matter. This is why plugging things in with the correct signs is going to matter, because if we didn't plug it in correctly, or we had the wrong sign on Q, we would get a positive W, and that would be the wrong answer. Okay, so we have to make sure we pay attention to our signs. Okay, let's try another one. Using your own table that you filled out in your lecture notes, calculate Q and determine whether heat is absorbed or released when a system does work on the surroundings equal to 64 joules and the delta U is equal to negative 23 joules. So pause your video and try this problem independently. So for this problem, we already know delta U. Delta U is negative 23 joules. And we know that the work is 64 joules. And we're solving for Q. So our language says that the system does work on the surroundings. So based off of that language, our work value would be negative. So plugging those values in as is, we get negative 23 joules is equal to Q plus negative 64. Now personally, because I care so much about the signs of my Q and my W, I like to keep that negative associated with that number. I don't like to, replace it, and so instead of writing Q minus 64 joules and replacing that positive with that negative, I personally just don't like doing that, just so I remember that I've already accounted for the sign in my Q or my W. So just a good kind of like best practice note there for you if you're getting kind of confused on these types of problems with the signs. Just don't try to do any fancy math moves where you're replacing negatives and positives and pluses and minuses or anything like that. So just plug it in as is. So we would then, let's do negative 23. In order to solve for Q, we would add 64 to the other side. So we get Q is equal to positive 41 joules. So now we want to know if heat is absorbed or released. Well, if Q is positive, that means that heat is being absorbed. By the system. Okay, so we did work on the surroundings and then we absorbed some heat to the system because Q ended up being positive. Let's do another one just for good measure before we finish up this lesson. Calculate W and determine whether work is done by the system or on the system when 98 joules of heat is released and the delta U is equal to negative 215 joules. So pause this video and try this problem independently, showing that you understand the concept. Based on the wording, the heat is being released, therefore Q is going to be negative. We already know that delta U is negative, so plugging everything in, we get 215 joules is equal to negative 98 joules plus W. Therefore, solving for W gives us negative 117 joules. And since work is negative, we then say that work was done by the system on the surroundings. Okay, so that finishes up our lesson on energy, energy changes, and heat. Move on to your next lesson where we will talk about the applications of our changes in energy and our changes in heat.